はい。では、続いてのご発表が、サンさん。
あ、はい、そうです。はい。
はい。東京大学の、サンさんで、タイトルです。こちら、コンポーネントワイズナチュラルグラディエントディセントトレーニングメソッド for the convolutional neural networks ということで、よろしくお願いいたします。
はい、よろしくお願いします。そうですね、先ほど、そうさんと同じ感じで、ちょっと英語で発表させてい
はい。
ただく。質疑が日本語は、はい、問題ないということです。はい、それでは、はい、よろしくお願いいたします。
お願いします。
Okay. Hello, everyone. My name is Sam Vanchan from Yoshimoto Laboratory, Tokyo. I would like to make presentation about my research topics, component-wise natural gradient descent training methods for convolutional neural networks. And yeah, I will start very general. Like neural network is a fundamental infrastructure for many advanced technologies in the modern societies. And among the various neural networks, convolutional neural network is a successful and widely adopted architectures. However, convolutional neural networks still present several significant challenges. And neural networks and also the convolutional neural networks are just a structure themselves. And unless going through a training process to learn the pattern from the data, they cannot predict the label on the input data. And the training process involves the training data sets and a learning algorithms called training algorithms. And the later, this training algorithms is the focus of my research. And neural network training can be considered a optimization of an extremely high dimensional in a extremely high dimensional space. And for example, the practical neural network can have million up to billions parameters. And the high dimensionality causes it impractical to find the global minimum for a neural networks. And the network capabilities depends on the training algorithm because each algorithm is optimized to different local minimas with different capabilities, and which motivates us to the motivation of our research come from the fact that the existing training algorithm produce minima with suboptimal network generalization capabilities. And in this research, we tackle this challenge by investigating a new training algorithms which optimize the network to minima with higher generalization capabilities. And here, so in neural network training, typically there are two training methods categories: first order and second orders. In the first order, the methods belong to the first order, quite straightforward. They follow the gradient descent to optimize the target functions. And in the second order categories, the methods belong to these categories. Trace the network curvature to produce more efficient parameter update. And the methods in these categories require fewer updates to converge, but it's also unpopular because of the expensive computational, but the expensive computations. And the most popular second order training methods is natural gradient descent, so-called NGD, which involve the calculation of a matrix called Fisher information matrix, so-called FIM. And I will explain more about NGD and FIM in the next slides. And NGD, by definition, is a precondition. The gradient and the gradient vector with inverse of the FIM Fisher information plus with a epsilon values. And the FIM, the Fisher information matrix, it has a square size of the number of network parameters, so it's very, very huge. And yeah, it contains correlations it contains the correlation of among the parameter of the networks, and obtaining all of the elements and inverse the full theme is very expensive and infeasible for practical networks. So this is where the general frameworks make it practical. So to make NGD feasible, the common approach is to approximate the theme in a block square shape. And this approximation is equivalent to decompose the parameter into group and apply NGD on each group independently. And the general framework, so-called blockwise NGD, accept any network parameter decomposition strategy and apply this approximation on NGD. And our proposed methods define as a special case of blockwise NGD with a new and specific network parameter decomposition strategy tailored for CNN, convolutional neural networks. And here we have, so in order to explain our methods more specific, we go with the, let me explain the structure of a convolutional neural network. So as its name suggests, it's composed by mainly by the convolutional layers. And this figure illustrates the mechanisms of a convolutional layers, and it uses a kernel to convolute the inputs spatially, like the elements stay near to each other, near together will be convoluted to an output, to the same output. So to collect more local features, convolutional layer is designed to have a multiple layer. So each operates on different input channels, and it also gives the output channel into different output channels. And specifically, the parameters on the same kernel highly correlated with each other, while the parameter with different input and output channels, they likely to stay far with each other on the calculation pathway of the networks. And these characteristics suggest our decomposition strategy on CW on our proposed methods. So in our proposed methods, we decompose the 4D tensor of the convolutional layers, and I will explain in the next slide. So here's our this slide mainly introduce our main contribution on my research. So the idea is to chain multiple decomposition levels. We first go with the neural network layers, similar to this already explored by other methods named K-fact, similar to that. Like in K-fact, it decompose the network by layers and then apply other methods for each layer, NGD. And for the output dimension layer, similar to the unit-wise NGD or the Tonga methods, it already decompose the network by the output dimensions. And our contribution comes into the next level, where we decompose the network's parameter after applying the decomposition on the network layer and on the output layers, we continue to apply it on the input layer. So the idea is pretty simple. And here we have, in general, each layer have the output, input, and the other layers. And we decompose the network by the layer first, and then go with the output layer and the input layer. And we leave the rest for the NGD, and we apply the NGD on the other layers, on the other dimensions of the network parameters. And we call this decomposition strategy NGD is component-wise natural gradient descent, or CWNGD. And we also find that CWNGD is well suited for the network where the parameters in small group highly correlated with each other in the network calculation part, such as in the convolutional neural networks, where we have the kernel here is quite small, and it fit very well with the calculation models and the computational powers of the current machines. And another contribution of our research come from the to make the practical CWNGD practicals. We propose a update mechanism, so-called sub-batch update mechanisms. So okay, let me like summary. In general, typically each when we separate the data on each process, it calculates the statistic. Statistic here is a gradient. It groups the gradient. It aggregates gradient, then calculate the feature information matrix and the update in the master process. But instead, we swap the order of the aggregation and the theme calculation, and we calculate the update earlier in each process. And within this update mechanism, we can maintain the stochasticity of the data in general, and thus we can improve the data, improve the generalization capability of the training network while we maintain the polarization capability of the training. So in the evaluation, I conduct several evaluation to find the optimal hyperparameter set for CWNGD by scanning the learning rate and damping rate. And I evaluate sub-batch update by evaluate accuracy before and after applying the sub-batch update mechanisms. And I conduct a cross algorithms comparison between CWNGD and existing methods such as ADAM, SAD, and KFAX by the number of epochs. And in the last experiment, I compared I did do a early measurements of the wall clock speed of the algorithms. And yeah, here are the list of experiments. Yeah, so it's for details. So let me skip this slide. And here are the models and data set I use in the algorithms. I test 1, 2, 3, 4 different network models and model families, and for each family, I iterate different network size to get a various to get the characteristic of each training algorithms. And for the data set, I use 1, 2, 3, 4, 5, 6 different data set, and I apply for each data set. I run with each model to get the comparison result. And here, it briefly introduced the implementation details. I used the Wisteria BDEC cluster, each node, each GPU, and thank you very much for the program support to support me on this research, and it helped me a lot. And I use the framework PyTorch with the distributed library and the NCCL for the communications. And for the I/O operation for each process, I use 7 CPU workers for the training data I/O. And this the result of the first experiment. We can for each learning rate and damping rate, I calculate the generalization accuracies, and the lighter the higher accuracies. So we can observe the big trend line here, and we focus on the number 3, where the second order methods in effect. So we can see that it works as expected, and we choose this points with a round number like 10 power minus 3 and 10 power minus 7 for the damping rate and the learning rate for the later experiment. So in the next, this one, like the results simple, like we compare the accuracy without and with sub-batch update, and we can see that in most of the case, with sub-batch update, the accuracy is improved. So the conclusion is simple, that sub-batch update improve CWNGD in general. And to understand the reason why like sub-batch update improved the the accuracies. We did another analysis on the, we intercept the minimizers given by the two algorithm variants, the one with subbatch and the one without subbatch, and we move from the minima with subbatch to without subbatch and inverse, and we can see that we have a sharp minimizer here and a more flat minimizer here. Explain why with subbatch update it gives higher generalization capabilities. And we did the same experiment on the 2D directions, and we got a kind of similar shape that for the subbatch update we have more flat the loss functions nearby the minima with subbatch update, and we got sharper loss landscape for the minima when trained without subbatch update. So let me go quickly. So for the trade-off, the number of process when applying subbatch updates, this is more kind of detail. So let me skip this result and move to this next one. And this one, we did another cross-algorithm comparisons. And we can see here, okay, sorry, I will go to the next slide, more details here. And yeah, we evaluate by the network families. We can see here for CWNGD, our proposed methods, it can provide a high and stable for all of the network models. So we test for convolutional neural network all this. So we can come to the conclusion that CWNGD can be the safe choice, the stable choice for any convolutional neural networks in general. Yeah. And so, okay, so next, in our research, we focus on the Goldilocks time we focus on the accuracy by the number of epochs, and this kind of an early evaluation on the Goldilocks time comparisons, where we train the image net within 2 hours, and we stop at 2 hours, and we compare the accuracies. We draw the accuracy graph achieved by each algorithms. And we have Adam with 72, Adam and SGD with 72 and 73 epochs, while with CWNGD just 68, a bit slower, but still competitive. And for the accuracies, CWNGD and Adam achieve the similar accuracy, while it go like with K-FAC stay far behind. And in conclusion, we propose a new neural network training algorithm, CWNGD. We theoretically explain that CWNGD is well suited for network with parameter correlating with each other in small groups, such as the convolutional neural networks. And we also propose subbatch update mechanism to remedy the issue of training network with a large batch size. And we did evaluation to confirm the, to empirically confirm the conclusions. And yep, and we also that CWNGD is superior to Adam, SGD, and K-FAC when training CNNs. And in future work, we want to make CWNGD a new and better standard for neural network training in general, and also evaluate on other architectures and evaluate the polarization methodologies. Yep, so thank you very much for your listening.